Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about steam turbines. So let's dive right into it. Well, before this, I've already made a video about thermal energy to electrical energy. There are many ways of doing it, primary of which were steam, thermoelectric generators, and basically Stirling engine. Now, steam is the backbone of our world, flat out. It's what we classify as power producer. So, if you are using electricity, there is a very good chance it came from a steam turbine, flat out. Like you can be anywhere in the world. You could be running on nuclear power, you could be running on natural gas, coal, or geothermal, whatever have you, or sometimes even concentrated solar thermal. Most of the time, you are running on steam turbine. So, this is a very big deal. And the turbines that we are talking about is also big, as in physically big, as in the size of a bus to a small building. It's huge. Now, the reason why we use steam systems rather than like steam turbine rather than any other system like Stirling or whatever have you is simply because steam turbines have ludicrously high power capability, aka you can make them huge in terms of power. Now, right now, the biggest I have found so far, it's capable of 1.5 gigawatts of output. Let that sink in. 1.5 gigawatt, aka 1500 megawatts of power from one point. So that's huge. This is the sole reason. Even if you can have something that is more efficient and it requires you to have like 116 hundreds of them, yeah, it's not economical. So that's the reality of it. Now, because we have been using this for quite some time, we know actual time-based data. It's like how long these puppy last. They can last for 50 years with good maintenance. And in terms of how long they can have, as in like on time, let's say a diesel power plant has to shut down every week or something like that. Turbine power plant, gas-based turbine power plants, they survive for like around 3 to 4 months before they have to shut down. Like again, it's not necessary they have to. They generally shut down to preserve and elongate life. These puppies, they generally work continuously for 2 to 3 years, and only after that they are generally replaced, simply because bearings require lubrication or some other sealing mechanisms require closer inspection. So before things get bad, you want to make sure you double check it. So they work very efficiently, they work for very long time, and they're very powerful. However, the consequences, they require high quality steam. What does high quality steam mean? High quality simply means the water cannot have too many dissolved gases, the water cannot have too much contamination, salts or things of that nature. Basically, you want quality material here. On top of that, in terms of how you are distributing it, it has to be equally distributed. It cannot be like, okay, I'm putting steam on the top and I'm not in the bottom. Like, you have to equally distribute it. The better you do these sort of things, the longer your turbine will last. Then we come to turbine types. Now, if you even roughly look around in the internet figuring out what kind of turbines are, there are generally two primary designs. One of them are impulse, another one is reaction. Now, impulse one, you can think of them, they are like a bucket, quote unquote. So steam falls on that, pushes it, like that's the system is. And then you have nozzle type. Now, each of them have their unique advantages. For example, impulse turbines are small, comparatively speaking. I'm still talking like giant fridge basically, and they are very efficient at high pressure. So if you are pumping YOLO amounts of pressure into this can convert them into rotational torque very efficiently. That's like its sweet spot. It got this. And in terms of pressure drop, it does not drop pressure too much. So like let's say you put 4000 psi, the exit would be around let's say 3000 psi. It will not go to zero. Now, while you take another system where you have nozzle based system, you can take input pressure which is like a few hundred psi, and the output could be almost vacuum. You can literally do that. So that is the reason why we have different architectures. So you have one small and powerful, then you have large and weak power. Now you may think, okay, why the heck, if this puppy can provide most of the power, why the heck we want to use this? Like, these are huge, expensive. The reason is these add up to 100 to 500 megawatts of power. Now you can understand that's a significant amount of power that you're like, yeah, I can pay for that. So that's why. So you generally have impulse, which are designed for high pressure turbine steam systems. You have reaction based, which is works based on medium to low, and then each of them have unique advantages. Generally, people just plug all of them. Now, for that reason, because you have to put many of them, you generally classify as the system as multi-stage. So if you go around anywhere in today's day and age, there is a 99.99% chance you have seen a multi-stage system. Now, generally, they are made of 3 stages. It can be more, it could be less, depending on the design, depending on the criteria. If the steam is not high quality, they might bypass the impeller design, simply because, again, it requires high pressure steam. So they might bypass this one and you only get the huge ones, the huge orange ones. So generally three stages are used. One of the high pressure stage is basically small, but it provides most of the torque. So if you have 1000 megawatt output, the around upwards of like 6 to 700 will be coming from this one point, basically the high pressure one. Then you have what we call steam that is coming out of it. It's no longer very hot or very high pressure. So we reheat that in the boiler, and that turbocharges it. Now doing that, we send this to medium system. Now medium system is not designed to like work on very high steam or very cold steam. It's like medium kind of. So output is also like medium kind of output. That is the second stage. And then the third, like the exhaust from the main system, basically the medium system directly goes into the low pressure one. At this point, because I specified the nozzle based design reduces pressure, so you can feed 1000 psi and the output could be literally near vacuum. So this directly feeds into the second system, where it extracts even the final amount of power that it can do, and that's the whole system. Like you have three systems: one high power, medium power, and low power, and they are invert in size. So smaller one would be the high power, medium one would be medium, and large one would be the weak one. So these are generally three systems. There could be more, there could be less, depending on the steam quality. Now we are talking about steam, and we are talking about something that is moving. So you must understand how the heck you are sealing something in that is like at 4000 psi. So because of the high pressure required, you need this puppy to be stable, because these things rotating mass, they can be as high as 60 tons. That's a very huge amount of mass, and if it's spinning and if it gets unbalanced, it's gonna literally destroy no matter which kind of casing you put on it. Like it can literally go through solid brick wall. So it is very serious. So balancing these puppy takes absolute precedence. Like they will take very long time to make sure that it's absolutely balanced. Now steam casing is generally kept independent. Wherever you have steam circulating in the system, it will be kept completely independent of bearings, because bearings and steams do not mix together, because bearings will have oil and they want to operate at colder temperature, and steam, well, it's hot. And not to mention it's corrosive, and not to mention it could literally set oil on fire indirectly. So you have to keep these two separate. Now how the heck you make sure you have a spinning rod going through a casing and still and have a high pressure steam without leaking it? Well, you can't. You technically can't. So what we employ is what we classify as Gland steam sealing system. So there are basically teeth and there are receiving teeth, and all of these teeth do not physically touch. They do not physically touch, and they are just acting as a resistance. Basically they are acting as a labyrinth. Now in this labyrinth, you put positive pressure steam into it. Why? Simply because in the low pressure side, specifically there, once the final stages of the blade has been exposed and is rotating, the steam is such a low pressure, it's almost partial vacuum. So air wants to rush in. You are talking about like 15 psi atmospheric pressure wants to go in. So to make sure that does not go in, first you have resistance. These teeth, basically the gland system, they act as a resistive barrier. On top of that, you put physical steam into there, where you're like, okay, I'm gonna flood this system with steam. The benefit of that is basically you are preventing what we call thermal shock. You do not want thermal shock, simply because even though your boiler room could be hot, it could be, let's say, 50 degrees Celsius or 60, the room where the turbines are, that could still be much cooler compared to the turbine, because turbine directly handles the high pressure steam. So a turbine would be, let's say, 300 degrees Celsius. So putting a 50 degrees Celsius air into 300 degrees Celsius turbine blade is gonna lose. So to make sure we put steam there, steam to steam, turbine pressure, temperature, all of them is stabilized. So that's the one thing. And Gland seal is not in like, okay, on the openings and closing of the casing. It's everywhere. Every stator fin and rotator fin has to have this, because you have to understand that you want steam to do the work on the blades itself, not leak around it, because again, everything wants to seek the least energy path, path of least resistance. Literally it will ideally flow through, flow bypassing it. So you want to make sure you do not allow the bypass. So Gland steam system is the main backbone that allows that. Then we come to the bearing blocks. Again, these are huge, heavy things. You want to make sure that you properly apply bearings to that. To make sure that the bearings are high quality, they generally are kept as a completely different enclosure. So you can have high pressure steam, medium pressure steam. In between, there will be a place just for bearings. It is the one that is carrying most of the load. And same will be like from medium pressure to high pressure, the medium pressure to low pressure. Basically, there will be another bearing block. That's how we are anchoring these things. Now they have thrust bearings, but ideally you do not want thrust bearings. Now what does that mean? That simply means rotationally bearings are good, but if your spinning mass that's spinning like this starts to go like this, yeah, you did. So to make sure that does not happen, low pressure also provides a unique advantage. You're gonna put low pressure directly in the center and it's gonna expand outwards. So it's like an X kind of turbine. You put steam, high pressure steam here, it expands on both directions. It's literally using steam as a pinning device. Basically it's pinning it in the main center, so it cannot do like this. That is why you will see like X kind of setup, because generally we think about turbines, we think we work from one side to another side. This is the reason why we make it into X. So you put high pressure in the center and let it expand outwards, so there is no requirement for thrust bearing. And now again, they will put thrust bearing, it will be just like it should not be used. It's like, okay, is there, it's ideally important. So these are the bearings and seals. Then we come to the material aspect. Now you have to understand this aspect, because of the general nature. Generally these turbines are kept at very high RPM and directly connected to the generator unit to improve efficiency. Because again, if you ask anyone, hey, give me a gearbox that can handle like 1500 megawatt, they're like, yeah, no. So generally we utilize a simple direct coupling, what we call. Now consequence of that is that generators RPM directly controls the generator's frequency. Frequency is important for grid stability. So your RPM gets locked. Like the RPM must remain same no matter what, because otherwise you could destroy the national grid. So 3000 RPM is kind of needed for 50 hertz system. So like India, you will need 50 hertz system. So our turbines will be spinning at 3000. Now if you are some European country that uses 60 hertz, you have to be spinning at 3600 RPM. And this is where the control mechanism is. So there is a lot of mechanism put in place for specifically detecting the hertz frequency. Why? Think of this: you put too much load into your electrical grid. So how the heck this maintains for that? First, this is a very heavy material. People want this to be heavy. The reason for that is if it's heavy, it will take time. Like you cannot, like inertia will help you smooth it off. So like let's say randomly somebody turn on, let's say, a very powerful metal melting style, like Smith kind of style. It's like randomly 1 megawatt power load has come into the generator. Again, the spinning mass will not slow down. Like physics will not allow it to slow down instantaneously. So during that time, the frequency will start to dip little bit. Like the 3000 RPM will start to go 2995. Like it will start to dip down. The moment computer detects that, computer will be like, okay, open up the steam valve because there is a spike. That's how we are stabilizing our grid, because this rotating mass is helping basically everybody. That's the sole reason the grid is stable, because these rotating mass, even if you have underload or overload, like let's say a scenario happened where you disconnected a large part of grid for something, power fault, lightning or something like that destroyed your substation, things happen. Again, it will not randomly start to spin up. Even though you reduce the load, it will still take time to spool up. So this rotating mass acts as a very good buffer. That's why we can even have a collective grid. Then we come to the steam part. Now steam is what we call supercritical. Now, so what does that mean? Simply means very, very high pressure. We boil water at very, very high temperature, around say 500 to 600 degrees Celsius. Now we're like, how the heck water is boiling at that temperature? Like, shouldn't water boil way earlier ago, like around 100 degrees Celsius? To make sure that it boils at 600, we put water under pressure, like a lot of pressure. Benefit, we get steam also, that is in ludicrously high pressure, 4000 psi. That's upper maximum, but you get the point. It's not a laughing matter. It's like very high pressure, and like this pressure is so high, if you directly blast it into a turbine on a single spot, it will destroy the turbine. So turbines are always kept spinning with some different independent motor system. There is a complete independent motor. It's just like never let the steam turbine idle to zero. Basically, it will always keep spinning like 1 RPM or 10 RPM. So it can instantly pick up because if the steam, that high pressure, high temperature steam directly hits it, the turbine blade is gonna go bye bye. And temperature, again, it's above 600 degrees Celsius. To handle this, we generally want 5% nickel alloyed steel. These are very good for the system, because we have been testing it, we have been making in 1950. We know the metallurgy which is required to handle it. Again, if somebody in the future can figure out some other metal alloy that is A, cheap enough, B, that can withstand higher temperature than this, we will get even more efficiency. Higher the temperature, the more the efficiency you get. However, because of the nature of the system, because you are steam, you're gonna oxidate no matter which material it is, no matter how stable it is. So we generally apply zirconium dioxide based ceramic coating. Now these coatings act as a primary layer of defense against oxidation, and over time, like that, specifically that 3-year period, you will generally open it and inspect everything. Is the coating working? Everything is all right. If everything is all right, good. If not, you're gonna reapply the coating and rebalance the wheel. So that's the reality of it. Like this material requirement, like it's a very complicated, and many times you may think, hey, can't we make better material? Yeah, but these are expensive things. Like these are for profit. This is not defense department where you can just do whatever you want. So you have to make it economical also. But the material requirement is complex. Now, if you want to go even more depth into the steam turbine architecture, I have provided some video down below, and there is one video series, whole series, that is directly taken from an actual power plant. Basically, the photos, the diagram, the CAD drawings that you are seeing, it's actually employed in real world. So detail on that puppy is on a different level. I would urge you to see that for more details, and even a video that is dedicated to just to seal management and all that jazz. So this was my presentation on steam turbine. I hope you liked it, learn from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me your disappointment, and please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.